Welcome to part 2 of Natural Language Processing Demystified. In part 2, we'll focus on deep learning for NLP. Deep learning is a subset of machine learning and focuses on extracting patterns and building representations from data using neural networks. So to understand deep learning, we need to understand neural networks. And in this module, we'll look at their core mechanisms, that is, the major things going on under the hood when they're being trained. And to further ground this knowledge, we'll then build a neural network from scratch in the demo. We'll also be touching on a lot of concepts we initially covered in the Building Models module in part 1. So if you haven't watched that yet and you're not familiar with the concepts there, please give it a view now. To understand neural networks, we'll start with the idea of a function. A function can be viewed as a machine that takes an input x, transforms it in some way, and produces an output y. Maybe the function takes an input and adds 1 to it, or maybe it takes an input and squares it. These functions can also be visualized with their input on one axis and the output on another. And of course, we could code up these functions easily as well. Now let's say we have a function that takes two inputs, x and w, and multiplies them together to create an output y hat. Let's say x is fixed. In this case, x equals 3 and cannot change, but w can vary. Lastly, there's a target value y set to 10. The goal is to adjust w so that the function's output y hat is equal to or as close as possible to y. To see what happens, we might start off setting w to 1, which results in an output of 3. Comparing the output against the target, we see it's off by -7. So we adjust w to 3 and see what happens. The function then outputs 9, and we're now off by -1, which is better. We're getting closer to the target. For the next attempt, we adjust w to 4, and now we're off by 2, which is worse than before, and this time we're overshooting our target. So we adjust back down to 3.2, which results in 9.6, and a difference of 0.4, which is the closest we've achieved so far. And we can keep making these adjustments to get closer and closer. Of course, we could have solved this problem analytically without any guessing, but it's here to illustrate a point. Conceptually, this is how neural networks learn. The x in this case would be our features. W is a set of weights, and we can view weights as a type of knowledge that this function is learning. It's taking input in the form of x, and it's being asked to learn a suitable w value to accomplish a goal, and it receives feedback to help it along. Another way to look at it is that it amplifies or dampens aspects of the input to help accomplish the goal. And the target is the label in a supervised learning dataset. To summarize the process at a high level, it starts by setting w to some initial value, for now assume it's random. The function output is calculated and compared against the target. Based on this difference, decide how to adjust w so that the output gets closer to the target, make this adjustment, then go back to step 2. And this loop is repeated until either A, some condition is met, for example, the difference between the output and target falls below some threshold, or B, a certain number of attempts is made. Now this process wasn't required for this initial problem, but when you have thousands of features and millions of weights, approximation through this trial and feedback process makes the problem tractable. No matter how many features and weights get involved, this process remains the same. In practice, neural networks go about this process in a much more structured manner, so let's start enhancing what we have. Going back to our simple function, we can visualize it like this. For the purpose of neural networks, there are two problems with the current function. First, this function describes a straight line that passes through the origin. So if w is set to 1, then the resulting line looks like this. This graph, by the way, is just for illustration and visualization. Now imagine if we wanted our function to learn a w value that best separated these two sets of points. This would be a binary classification task, and y hat in this case could be either 0 for green or 1 for blue. We'll talk about neural networks for binary classification later in the video. In this case, the function wouldn't find a good fit regardless of the w value. W set to 1 wouldn't work, and neither would w set to 2. With a line that's forced to go through the origin, it's difficult to find a decision boundary that effectively splits the labels in this distribution. The standard way to get past this is to introduce a bias, symbolized by b here, which allows us to translate the line up and down the y-axis. The function then would be tasked to learn values for both w and b until a good fit is found, which makes a clean separation now possible. The other issue is that this function can still describe only linear relationships. Imagine we wanted our function to learn another decision boundary, but this time, the data points are distributed like this. in this case the bias alone isn't enough. We need something more to help us describe nonlinear relationships. To deal with this, we can introduce a nonlinear activation function. That is, after performing the linear combination and outputting the result, which we'll call h, we run h through another function, which then produces y hat. And this function can take on many forms. 3 popular nonlinear functions for neural networks are shown here. If you haven't seen them before, don't worry about it because we'll go into detail about them in the next module. For now, the important thing to know is that they enable us to model nonlinear relationships. Going back to our original problem, by adding a nonlinear activation function and by chaining multiple functions, as we'll see later, we can arrive at a more suitable decision boundary. Okay, so we've taken our original function and added a bias and an additional nonlinear activation function to help us model more complex relationships. This is what we have right now. Let's clean up the representation a bit. We'll symbolize x times w with this sigma symbol here, the activation function with phi, and finally include the bias as a separate input. What we now have is the fundamental building block of neural networks. Some people call it a unit or a node, which are terms I prefer because wherever I can, I like to get away from biology-inspired terminology, but others call it a neuron. And by combining these units in various ways, it gives rise to neural networks. Neural networks have been around for decades, but their popularity fluctuated because of certain shortcomings. But a few true believers kept working to refine them when most were dismissing the concept, and today modern neural networks have led to incredible breakthroughs in image recognition, language translation, and media generation, whether it's images or text, among other things. One note here, you might see something like this called a perceptron in the literature. Keep in mind that the classic perceptron from the 1950s technically does not have a nonlinear activation function, but rather uses a step function, so we're not using that term here. Alright, let's keep building on this. As we've seen, there's almost never just one feature involved. In a given dataset, we can have anywhere from a dozen features to a few thousand, as we had in our vocabulary from earlier demos. Here we have an example with 3 features as inputs being fed into the unit, with each feature accompanied by its own weight. Each weight then would be adjusted individually to produce an output as close as possible to some target given an input. Perhaps feature x1 is discovered to be very important, and so the weight on that goes up, while feature x3 is discovered to be less important, and so the weight on that goes down. There is still only one bias term. When there are multiple features and weights involved, the sigma step is a dot product and an addition. In this example, let's say x is a feature vector with values 1, 2, 3, the respective weights are 4, 5, 6, and the bias is 7. X and w would be dotted, and then the bias added. The result of this would be passed through the activation function. Note how the weight vector is a column vector rather than a row vector like the features. That is, the weight vector is assumed to be transposed. This is the convention we'll stick to in this module, but in literature elsewhere, you may see the weights presented as row vectors, which are then transposed when used in the dot product. We'll go over this again shortly. A note about the bias, we can keep it as a separate addition step. Alternatively, we can include it as part of the dot product by adding a 1 constant to our feature vector with its own weight, w sub 0. The neural network would then learn w sub 0 as its bias, and it works out to be the same thing. I prefer this approach as it makes everything cleaner. Now what we have here is still ultimately just a function. The result y hat is just an application of some activation to a dot product between features and weight. And because it's a function, it means we can chain and compose layers of units into neural networks to approximate ever more complex functions. In simple terms, if a function transforms inputs into outputs, then layers of these units working together can help us find more complex transformations between inputs and outputs. For example, a transformation of an input image to a label output, with the label maybe describing what's in the image. Let's look at composing neural networks. Let's say you have a dataset with 2 features. In a neural network, the first layer is the input layer. Nothing happens in those green circles you see there, they just represent inputs going into the neural network. What we can then do is send those inputs to a unit. Those inputs are dotted with their respective weights. The result of that operation goes into the activation function, and the result of that is the unit's output. Note how we've included the bias here as well. Using our style, the bias of 1 will be multiplied by its own weight. The bias is shown here explicitly, but in most neural network diagrams, they're omitted and assumed to just be there. Okay, so what we have now is exactly what we've seen up to this point, but we don't have to stop there. We can add more units, and this constitutes a layer. In this case, we're adding 2 more units, and both are also receiving all inputs. The number of units in a layer is called the layer's width. Any layer between the input and output layers is called a hidden layer. In this case, it's also a dense or fully connected layer because each unit is receiving every output from the previous layer. Dense layers are probably the most common type of layer you'll encounter. From there, we can add more layers if we think it's suitable. In this case, we're just forwarding all output from the hidden layer to a single unit, which then produces the final output. This final layer is the output layer. Note how each output from the hidden layer is accompanied by its own weight. This means the neural network will be adjusting weights from the input to the hidden layer and also weights from the hidden layer to the output layer. This is an example of a 2-layer network. It's 2 instead of 3 because by convention the input layer isn't included. You may be wondering how many layers we should have in a neural network and how wide each layer should be. The width and depth of a neural network would be part of its hyperparameters, and there's no clear answer to it, but we will explore this more in the next module. This diagram may look pretty abstract, but under the hood, it describes a series of matrix operations. Let's put the diagram to the side for now. With our bias notation, our feature vector for a single example would look like this, with x sub 0 representing the bias input set to a 1 constant. The weights would be a 3 by 3 matrix because there are 9 weights between the input and hidden layers. Some clarification on the notation here. The superscript WL represents the layer index. In this case, all the weights belong to the first hidden layer, so the layer index L is 1. The first subscript I represents the from unit in the previous layer, and the subscript J represents the to unit in the current layer. So in this weight matrix, the first column holds the weights going from each unit of the input layer, so units 0, 1, and 2, to the first unit in the hidden layer. In other words, the first column holds the weights of the first unit in the hidden layer. The output from the hidden layer is generated by doing a dot product between the inputs and the weights. Since we're dotting a 1 by 3 vector with a 3 by 3 matrix, the result should be a vector of 3 components, represented here with A1, A2, and A3. So A1 is generated by doing a dot product between all the initial inputs and the weights of the hidden layer's first unit, and running the result through an activation function. A2 is generated in a similar way. The inputs are dotted with the weights going to the hidden layer's second unit, and the result is run through an activation function. And so is A3. The inputs are dotted with the weights of the hidden layer's third unit, and the result is also run through an activation function. And almost always, all units in the layer use the same activation function. The resulting vector then is the output of the hidden layer. Okay, before we go further, there's an important note about implementation. The weights here are set up as column vectors, that is, they are transposed to make it easier to understand. At least, I think it's more natural. In other sources, you'll often see weights presented in a row format and then transposed during the dot product operation. And sometimes you'll see the subscripts in reverse order as well. The important thing to know here is that no matter the notation in the order of operations, as long as it's consistent throughout, the concepts and outputs remain the same. Generating the final output of the neural network is a similar deal. The hidden layer output, along with the bias this time, is dotted with the output layer's weights to produce y hat. This type of neural network is known as a feed-forward neural network because data flows only one way, and it's likely the most common type of neural network you'll encounter. And you may have noticed there's no activation function in the output layer in this example, and depending on what we're doing, there may or may not be. We'll look at both cases. Let's look at a few ways to compose simple regression and classification networks and introduce loss functions. Say we want to train a neural network to predict housing prices, and our data set has 2 features, square footage and number of bedrooms. In real life, we'd certainly have more, such as number of bathrooms, lot size, average income for the zip code, and so on, but we'll keep it simple and say we have 2 here. I'll also omit the bias term this time, but assume it's there. We'll add a hidden layer and a simple output layer. And for now, just assume the weights are initialized randomly. We'll explore weight initialization more in the demo and the next module. The output layer doesn't have an activation function because there typically isn't one in a regression problem. Instead, it just outputs a linear combination of the previous layer's output and its weights. And the output itself is the network's prediction for the house price given the input. Given this is a supervised learning problem, our dataset is labeled with the real price. So our network is tasked with learning weights that best transforms the house feature's input to a price output as close as possible to a target. in this case, the real price. To help the network along, we need to calculate the loss, that is, the difference between the prediction and the target, and use that information to train the network. This is where loss functions come in. There are a variety of them, and which one we use will depend on what we're trying to do. A popular one for regression is the mean squared error. It's simply the difference between prediction and target squared. Squaring the difference amplifies big errors. This formula is for a batch of predictions where n is the number of samples. So squaring the difference also avoids them canceling out when taking the average. Say we have a dataset of 3 labeled examples and the network made these predictions. The MSE for this batch would look like this: each prediction minus its corresponding target squared. These values are all added up, then divided by the number of examples. And the batch loss in this case would be 12,708.3. The goal is to have the network adjust its weights to minimize this value. In addition to MSE, other popular loss functions for regression include mean absolute error, which may be more suitable if your data contains few to no outliers and you don't see a need to penalize larger errors. The Huber loss is quadratic when the loss is below some threshold and linear otherwise, which makes it less sensitive to outliers. I've included links to both these loss functions, and I suggest reading about them after absorbing the content in this module. So going back to our network diagram, we can plug in the mean squared error loss and get the loss value. This step where inputs go into the network, transformations take place, outputs are generated, and a loss is calculated is called the forward pass. Let's take a look at another example, this time for binary classification, let's say to identify spam. Same idea, we could have a number of incoming features such as words, sender email address, IP address, etc. Here we have a 4-unit hidden layer, which then feeds an output layer. This time note that there is an activation function on the output layer, and for binary classification that's typically a sigmoid function. We're going to go over activation functions in detail in the next module. The important thing to note for now is that the sigmoid function takes some input x and outputs a value between 0 and 1 inclusive, which maps well to a task where we're calculating the probability of something. So y hat is going to be some number between 0 and 1 inclusive, representing the probability of the input being spam. The label is just 0 for not spam or 1 for spam. And we compare the two to determine the loss. What's the loss function here? In this case, what we're interested in is correct labeling rather than some continuous value. A common loss function for binary classification is cross-entropy loss. I've included a link explaining cross-entropy at greater length if you're interested, but at a high level, cross-entropy is one way to measure the difference between 2 probability distributions. Now, this cross-entropy loss function may look involved, but it's simple. Look at the target y in this function. When the target is 1, the part of the calculation after the addition results in 0, so it can be dropped off and we can focus only on the first part, and that's just y times the log of y hat. When the target is 0, it's the opposite. The part before the addition becomes 0, and we can focus on the part after it. Let's say we have 3 examples in our dataset, and these are the predictions and targets. And this is what the calculation would look like. The first 2 targets are 1, so we take the log of the predictions. The last target is 0, so we take the log of 1 minus a prediction, and divide the whole thing by 3 since we have a batch of predictions. Note the negative sign to flip the loss value so that it becomes something to minimize. In this case, the loss is 1.53, and the goal again is to adjust the weights to minimize this value. And at a glance, we can tell the first and third predictions are pretty good, but the second one was off. So going back to our binary classification network, we can plug in a cross-entropy loss function that would enable doing forward passes on our network. Okay, one more example. Let's say we need to do some multi-class classification, such as classify a document into one of 3 classes. Once again, we have some incoming features feeding into a fully connected hidden layer with 4 units. The output layer this time looks different. We're going beyond binary classification, and in this case, trying to determine which of 3 classes a document belongs to. Consequently, we have 3 units in the output layer, 1 for each possible class. And this generalizes. If we're trying to classify a document into one of 10 classes, our output layer would have 10 units. Each unit in the output layer will output a value we'll call Z1, Z2, and Z3 respectively. Somehow we need to translate these 3 Z values into a Y hat value, which we can use to compare against the targets and calculate a loss. The solution is to use something called a softmax function, which is a generalization of the sigmoid function we saw earlier. The softmax takes n inputs and converts the inputs into a probability distribution, which adds up to 1. Here's the softmax equation for a single component or z value. The numerator is the natural exponent raised to the power of z sub I, and the denominator is the same calculation for all the inputs added together. Let's look at an example to illuminate this. Let's say these three values are what our network outputs. The denominator would be calculated like so: e to the power of 0.3 plus e to the power of 1.1 plus e to the power of 2, which works out to 11.74. The individual components then would be calculated like this. Each numerator is e raised to the power of the respective z component. And that leads to this probability distribution where the components together add up to 1. In this case, the network outputs a prediction signaling the third class is the most probable. Okay, so that's the softmax function, and we're going to see it throughout this course. Okay, so y hat in this case is going to be a probability vector. That leaves us with selecting a suitable loss function. And on a related note, what would the target y look like in this case? For multi-class classification, we can use cross-entropy loss as well. In fact, the binary cross-entropy loss function we used was a special case of the categorical cross-entropy that we'll use here. Our predictions are going to be probability vectors. In this case, we have predictions for 4 samples. The corresponding labels would look like this. That is, each label would be a vector of length equal to the number of classes, 3 in this case, with the correct class position set to 1, and the rest set to 0. This labeling scheme is called a one-hot encoding and can be used with any kind of discrete data. This is the categorical cross-entropy equation for a single example, not a batch, but a single example where k is the index of a vector component. So calculating the CCE between the first prediction and target just involves an element-wise multiplication between y and the natural logs of y hat, and adding it all together. In this case, the loss for the first example works out to 0.46. But notice that only one of the likelihoods actually matters, in this case the last one corresponding to the correct class. The other probabilities just multiply by 0 and drop out. So really, we can just calculate the negative log likelihood for the positive class and ignore the negative classes altogether. This equation then is the categorical cross-entropy for a batch of examples. It's simply what we did just now, but divided by the number of samples. The k subscript is the correct class, and I is the sample index. Working out the math for this batch looks like this: natural log of 0.63 plus log of 0.55, and so on, all divided by 4, which works out to 0.98, and once again, the goal is to adjust the network weights to minimize this loss. And at a glance, we can see a big chunk of the loss is coming from the third sample, where the probability for the correct class was only 7%. Like regression, there are alternative loss functions for classification as well. One is hinge loss for binary classification, and where the labels are -1 and 1 rather than 0 and 1, and it emphasizes the error when the signs are different rather than probability estimations. For multi-class classification, an alternative is the Kullback-Leibler divergence loss. Like cross-entropy, it's also a way to quantify the difference between two distributions, but KL has the nice property of being 0 when two distributions are identical. And beyond classification, it's preferred in situations where you need to directly know the difference between distributions, such as in autoencoders. I've included links to both loss functions in the notes. Going back to our classifier diagram, plugging in a categorical cross-entropy completes the network, and now we can do forward passes on it. Now, as we've said over and over again, after we've computed the loss, the next step is to adjust the weights such that the loss goes down, which hopefully translates to a better performing model, whether we're judging by accuracy or something like precision or recall. Let's dive into that now. Going back to the example we started with, we had this function where we wanted to find some W value that would make the function output match or get as close as possible to the target. And what we did was just use common sense. We just started with a random value and just kept adjusting it based on the difference after each attempt. But our computers need a clear, systematic algorithm to follow in order to do the same. Here we have a table of 4 attempted W values, the corresponding Y hats, and the resulting loss values calculated using mean squared error. We can plot the relationship between the W values tried and the subsequent loss. When W was 1, the loss was high, and it got progressively lower as W increased until it started rising again. Note how the lowest point on this curve corresponds to the W value that led to the lowest loss value. To make it clearer, here's a larger table of W values attempted and the corresponding losses. Once again, the lowest point on this curve corresponds to the W value that led to the lowest loss value. Here's the key point. If we can figure out how changing W affects the loss, and specifically how it can lower the loss, then we can use this information to adjust W accordingly. And we do have that information. We can use the derivative of the loss function to measure the sensitivity of the loss with respect to W. Let's take a look at that. So this is our loss function. Note here for simplicity that we're not using the batch loss, so there's no dividing by n. This is the loss for a single example. If we expand y hat, we get the original equation x times w. And by the chain rule, we arrive at the derivative. X and y are both static in this case, so this effectively tells us how the loss changes for every unit change in w. We now have everything to algorithmically update w. Here, w sub t plus 1 just means the next w value to try. Think of t as the timestamp, so t plus 1 is the next timestamp. And alpha is something called the learning rate. We're going to talk about learning rate a lot more in the next module, but for now, treat it as a way to control how big of a change to make in w. So to update w, we'll simply take the current w value and subtract it by alpha times the derivative of the loss with respect to w. We're subtracting because we want to travel down the slope towards lower loss. Let's look at an example to really anchor this. So here we've set x to 3 and y to 10 as before, and the learning rate alpha is set to 0.01, which is a popular default, and I've pre-plotted the loss function to help with visualization. Say we start randomly with a w value of 0.5. If we calculate all the other cells, we get a loss of 72.25, which is plotted as a circle on the graph. We also get the next w value to try according to this algorithm, which is 1.01. If we try 1.01 and work out the numbers, we see we get a lower loss as well as the next w value to try, which is 1.43. So we'll try that, and that's what we get. Next step, the loss lowers further, and further some more. Notice how the loss is changing at a decreasing rate, which visually corresponds to the gradual flattening of the curve. And if we keep doing this, we'll eventually arrive at a w value of 3.22 and a loss of 0.12, which may be good enough. What we've done here is started with a random w value and systematically calculated new w values, which led to an ever-decreasing loss. It's common in the literature to compare this process to a ball rolling down a hill, but formally it's called gradient descent. Gradient descent is a general algorithm for iterative optimization and isn't something specific to neural networks. In the example we just worked through, we just had a single w, but in a neural network we certainly will have more than one. State-of-the-art networks have billions of weights and keep growing. When we have more than one weight, we need to find the partial derivative of the loss function with respect to each weight. In this illustration here, that's w1 and w2. With two weights, the loss surface is three-dimensional. This gives us the gradient, which is a vector of partial derivatives and where the gradient in gradient descent comes from. It gives us the direction of steepest ascent, so when we perform gradient descent, we subtract to go in the opposite direction. Let's work through an example. So here we have a classification network with no hidden layer, which makes it the equivalent of a logistic classifier. The loss function is the cross-entropy loss. Once we perform a forward pass on this network, we want to calculate the gradient so that we know how much to adjust each weight by. In this case, we have three weights, so the gradient should have three components. So this last component is the derivative of the loss with respect to w2, or how much a change in w2 affects the loss. To make it easier, we'll break out this unit into its two separate steps. H is the value from the linear combination step, and y hat is what we get when we run h through the sigmoid function. Doing that leads to this. Let's say we want to know how a change in w2 affects the loss. What we did in the previous example with the single w value generalizes here. It's just a bit more involved. One useful way to think of the forward pass is as a chain of influence. So a change in w2 affects h, a change in h affects y hat, and a change in y hat affects the loss. In a similar fashion, rather than calculating a final derivative all at once, we can work backwards and use the chain rule to calculate how each immediate input affects the output at that point. We can look at how the loss function changes with respect to y hat, how y hat changes with respect to h, and how h changes with respect to w2. The derivative of the loss with respect to W2 then is these individual derivatives multiplied together. Let's work through an example to anchor this further. Say we have a single example input, and the values of our two features are 2 and 3 respectively, and there's a constant bias input of 1 as well. The weights are 0.1, 0.2, and 0.3 respectively, and the target y for this example is 0. Here below are the equations for the sigmoid function on the left and binary cross-entropy loss function on the right. Note we're just processing a single example here, so there's no averaging on the loss function. Plugging in the numbers, h works out to 1.4, y hat to 0.8, and the subsequent loss is 1.62. We want the network to adjust the weights so that on the next forward pass, we get a lower loss. To do that, we need to work backwards to calculate individual derivatives between each calculation hop. Let's focus on W2 for now. Here are the derivatives below, with the derivative of the sigmoid function on the left and the derivative of the loss function with respect to y hat on the right. If you're curious about how these derivatives are derived, I've included links on the module page. If we work it out, we arrive at these values for the individual derivatives. The derivative of h with respect to W2, by the way, is just whatever the input was. In this case, 3. Calculating the loss with respect to W2 then is a matter of multiplying the derivatives together, which works out to 2.43. If we follow the same procedure for the other weights, we get 0.81 for a W0 and 1.62 for W1. And that is the gradient following this forward pass. Now, a few critical things to note here. First, all the major frameworks handle this for you under the hood, and there is no need to tediously calculate all this by hand. Second, notice the presence of repeated derivatives in the calculations highlighted in yellow. To recalculate this each time by hand would be a waste, so critical optimization would be to cache these derivatives, and that's what frameworks do under the hood. These frameworks structure the network as a fine-grained computation graph where each calculation is broken down into granular operations, and the results of both the forward pass and intermediate grading calculations are cached in the data structures of each unit. This way, there's no need to recalculate the results of repeated derivatives over and over. This process is known as autodiff, and I've included a link in the notes if you wish to learn more. This process of calculating the derivatives and saving the results as we work backwards is called backpropagation. Essentially, it's a combination of the chain rule and dynamic programming. If you're not familiar with dynamic programming, it's an approach to algorithmic problem solving where the final solution is built up from solutions to smaller problems, as we're doing here. All right, let's finish this example. So we have our gradient now. The equation for the update step is the current weight minus the learning rate, alpha, times the gradient. Assume alpha is set to 0.01. If we work it out, we get the next weights to try. 0.09, 0.18, and 0.28. So all the weights are lowered in this case. So we'll update the weights, and if we work it out, h is now 1.29, y hat is 0.78, and the new loss is now 1.53, a drop from the previous loss of 1.62. And that's what it means for a neural network to learn. Under the hood, it's a repeated cycle of forward pass to see what the loss is, backpropagation to calculate the gradients, and gradient descent to update the weights, repeated over and over until some criterion is hit. Now, what if we have multiple layers? Here we have a 2-layer network, and let's say we want to update a weight in the first layer. In this case, the weight going from the last unit in the input layer to the last unit in the hidden layer. What we went through generalizes here as well. This time it's just a matter of calculating and multiplying a longer derivative chain. We're going to tackle this scenario in the demo. So now that we know the core mechanisms of neural networks, what's really happening here once we strip away any mysticism? At its core, the neural network is searching for transformations that convert the input x to the desired output y. And it does this by adjusting weights to emphasize or de-emphasize features as needed. So for example, if you're predicting used car prices, the network may learn that mileage and year are important features, but the number of cup holders is not as important, and adjust the weights accordingly. And the hope is that once the network sees enough examples and goes through this training process, it'll then be able to accurately predict the prices of cars it hasn't seen before. In that sense, the weights it learns can be seen as a form of knowledge, but really they're hard to interpret. Each layer in the network learns some representation of its input. Going back to our used cars example, maybe one unit in a layer is learning about the impact of brand, another unit is learning the impact of mileage, a unit further in the network may then learn the impact of these two features considered together, and so on. But neural networks are often black boxes, and gaining some interpretability is an ongoing research area. It's time for a demo. Let's take everything we've learned so far and use it to build a neural network from scratch. Okay, so here I've opened the NLP Demystified Neural Networks Foundations Colab notebook. You can access it through either the module page or the NLP Demystified GitHub repo. What we're going to do is build a neural network from scratch, and we'll do this in 2 phases. For our first phase, we'll perform a forward and backward pass step by step, right down to the dot products. And by backward pass, I mean backpropagation. And on every step, we'll examine the inputs and outputs to get a sense of the flow, the matrix dimensions, and the reasoning. In the second phase, we'll encapsulate the operations in a set of classes and compose them into a simple neural network, which we'll then train. Alright, here's the dataset we'll use. The dataset has 5 examples in it. The input has 3 features, and the targets are binary true-false labels. So the target for the first input is false, and so on. I made this dataset up and it has no sense to it other than vaguely low numbers mapped to false and higher numbers mapped to true. So this is a classification task where the network needs to learn how to classify an input into either true or false. Unlike in the slides, we're going to work with batches of data. That is, we're going to process multiple inputs at a time rather than single inputs, and this will help us get more comfortable working with matrices. It's also why the inputs are being assigned to this capital X variable here, which is convention. This is what the network is going to look like. We'll have our input layer with its 3 units because each input has 3 features. We'll have a hidden layer with 4 units and its hidden weights. The hidden layer will also have an activation function, and because we're classifying into one of 2 categories, we'll have an output layer with 2 units, also with its own set of weights. The output from that will go into a softmax, and we'll use the result to calculate a loss. A few notes here. We're going to add biases explicitly in our examples. In the slides, we talked about including biases as a constant of 1 with its own weight, but here, we'll keep them separate and add them. I'm doing it this way because it's just more explicit. Also, when we discussed binary classification in the slides, our example showed a single output node with a sigmoid activation function, and we used cross-entropy to calculate the loss. But here we have 2 output nodes going into a softmax activation function, and we're using categorical cross-entropy to calculate the loss. And this setup is usually used when we're doing multi-class classification, so tasks with more than 2 classes. So why are we doing it here? It's just because this setup is more common in NLP, and it's okay to use it even for binary classification because the softmax is a generalization of the sigmoid, and categorical cross-entropy is a generalization of binary cross-entropy. And this way we get exposure and practice with the setup, that's all. Okay, so this is the architecture we'll follow. Alright, so you may recall from the slides that when we were using softmax and categorical cross-entropy, we need to one-hot encode the targets. To create our one-hot encodings, we'll use NumPy's unique function to find the unique values in our list of targets and create indices for each target value. So here we have 2 unique values in our target list, false and true. And this return inverse parameter here returns a list of indices corresponding to each value in our target list. So false is assigned an index value of 0, and true is assigned an index value of 1. And we'll use this list shortly. Next, we'll create a matrix of zeros for our one-hot encodings. In this case, the dimensions of this matrix will have rows equal to the number of samples, so 5, and columns equal to the number of classes, so 2. Alright, we can now create our one-hot encodings. aRange is a function that creates an interval similar to the range function in Python. And we'll index into our zeros matrix using aRange and the indices, and set those positions to 1. And what we get are our one-hot encodings. So the first target is false, so the first index of the first encoding is set to 1 because it corresponds to false. The second target is true, so the index is set to 1 in the second encoding, and so on. Alright, let's do a forward pass. We'll start by setting a few variables here. The shape of our input is 5 by 3, 5 samples, 3 features each. And we're going to have 4 hidden units. Alright, we need to initialize the weights of our hidden units. We're going to cover weight initialization in more detail in the next module, but for now, we'll keep it simple. We'll initialize our weights randomly from a uniform distribution. We're going to have 3 input units feeding 4 hidden units. So the weight matrix dimensions are going to be 3 by 4. And we'll say more about this in a bit. We're also going to constrain the size of weights to be between minus 0.5 and 0.5. This is because weights that are too large can lead to something called exploding gradients, and weights that are too small can lead to something called vanishing gradients. Again, more about this in the next module, but for now, this simple approach will suffice. Lastly, we'll also declare a bias array of 4, all initialized to 0, which is common practice. By the way, I set the random seed here because that way the weights will be initialized to the same value every time, and that way you and I will both get the same results. But if you want the weights to be different, just comment out this line. Alright, so here are our initial hidden weights. And these are the shapes that we're working with so far. Alright, something important to keep in mind here that we also discussed in the slides, the convention we're using has the weights transposed. So each column of the weight matrix holds the weights for a single hidden node. In this illustration here, each input feature, which is in row format, is going to be dotted with each weight of the first hidden node highlighted in orange, which is in column format. In other resources, you may see the weights presented in row format and then transposed only during the dot product operation. Alright, so just to be sure, these are the hidden layer weights, and each column holds the weights of one hidden unit. So the first column holds the weights connecting the input units to the first hidden unit. Alright, let's start the forward pass. As we saw in the slides, the first operation is the linear combination of the inputs, weights, and biases. The input is dotted with the hidden weights. This creates a 5 by 4 matrix, and then the biases are added to each row of that matrix to create H1. Keep in mind that each row here represents a sample from the input. So this represents the first sample, and this represents the second sample. This is the output of the first unit for the first sample. This is the output of the second unit, and so on. Now, we need to pass H1 through an activation function. We'll use a function called ReLU, or rectified linear unit. We didn't cover this in depth in this module, but we will in the next. For now, just know that it's the most popular activation function for hidden layers for a variety of reasons, and it's simple and cheap to calculate. The ReLU simply takes an input, and if it's greater than 0, it'll pass it through. Otherwise, it'll output 0. And that's described by this function here. That's it. So if you pass in 5 to the function, it'll output 5, pass in 10, it'll output 10, pass in -1, it'll output 0. And we can get this behavior using NumPy's maximum function, which will apply to every component of H1. And this is our output. So this is H1, and this is A1, the result of our ReLU. Anything negative in H1 results in a 0 in A1, while the rest of the values are just passed through. So very easy, and you may be wondering why this function would even work to add non-linearity. Essentially, the ReLU is adding a bend in the linear function. And the more layers and units we have with ReLUs, the more bends get added. With enough bends, we can approximate nonlinear relationships, and the network learns to adjust the bends as needed to get closer to the target. A1 then is a 5 by 4 matrix and is the output of our hidden layer. Alright, so next, we need to generate the output of our network. So we'll take the hidden layer output and pass it forward to the output layer. For that, we'll need to initialize the output layer weights. We have 4 hidden units feeding 2 output units. So our output weights will be a matrix of 4 by 2. And once again, we're constraining the weights to be between -0.5 and 0.5. We also have a bias vector of 2. These are our output weights, and these are the shapes we're working with right now. Just as we did with the previous part of the forward pass, the hidden layer output is dotted with the output weights to create a 5 by 2 matrix, and the bias is added to each row of that to create H2. And once again, each row here represents a sample. Alright, where are we? Now we need to run H2 through a softmax to turn each row into a probability distribution. Recall the formula for softmax from the slides. For each row, it's a matter of exponentiating e to the row component, then dividing it by the sum of all the exponentiated values. Let's focus on the numerators first. We can just use NumPy's exp function and apply that to every component of H2. That looks straightforward, but there's an issue here. Exponentiated outputs increase rapidly relative to inputs, and once we get to a certain input size, we get overflow. Here, trying to exponentiate e to 1000 results in this inf value. To deal with this, a common tactic is to subtract each row component from the maximum value of that row. To get the maximum value, we can use NumPy's max function, but this returns the maximum value from the entire matrix, when what we want is the maximum value from each row. So to find that, we can specify the axis. In this case, setting axis to 1 results in a vector holding the maximum value from each row. But there's still another problem here. When we go to subtract each row's maximum from that row's components, we'll get an error. This is because the shapes aren't set up in a way that allows broadcasting. Going back above, we want to subtract the first sample's maximum from the first sample's first component here, and the second sample's maximum from the second sample's first component here. And we want to do the same thing with the second column. In other words, we're doing a column-wise subtraction, right? But the maximums are currently in a single row, and the subtraction operation is trying to subtract a row of 5 from rows of 2, which doesn't work. So what we need is to store our maximum values in a column format, and we can do that by setting keep dims to true, which retains the original outer dimension. Okay, so now our maximum values are in column format. And now when we perform the subtraction, it'll apply column-wise, and we get the numerators. Next, we'll calculate the softmax denominators, and that's a matter of summing each row with axis set to 1, and because we'll be dividing column-wise, setting keep dims to true. And with a quick visual inspection, we see the results are correct. Finally, to calculate the softmax output, we'll do the division itself. Okay, so this is our final y-hat output from the network. Each row represents the network's classification for a sample. So for the first sample, it's classifying false with a probability of 42% and true with a probability of 58%. In this case, it placed greater probability on true for every sample. Now that we have our y-hats, we need to calculate the categorical cross-entropy loss between y-hat and y. Alright, so recall the formula for CCE. This is the full non-shortcut version. K is the component index, and I is the sample index. We're using the full non-shortcut version just to keep things more explicit. To make it clearer, we'll print out the targets y and y-hat. Okay, so to calculate the CCE, we'll do an element-wise multiplication of each y row component with the negative natural log of its corresponding y-hat row component and sum it. So 1 times the negative log of 0.42 plus 0 times the negative log of 0.58 and add them together. That'll give us 5 values. We'll then take the average of those 5 values, and that's going to be our loss. Okay, down here, we're doing the component-wise multiplication and then summation of each row. We would then take the average of these values to get our loss. Now there's a potential issue here. We're taking the negative log of every y-hat component, but what if one of them is 0? In that case, we'll get an inf value here. So to deal with this, we'll clip our values so that the lowest value will be a tiny number, and the highest value will be a number just below 1 since y-hat is a bunch of probability distributions. We could pick these numbers arbitrarily, but we'll use the NumPy finfo function to get the smallest possible float number on our machine. So this is the smallest float possible on this machine, and the upper bound will be 1 minus that. To perform the clipping itself, we can use NumPy's clip function and pass it the array and lower and upper bound. So here 0 gets clipped to the lower bound, and 10 gets clipped to the upper bound. And now, when we try to take the negative log of the clipped example array, we don't get any issues. Okay, so let's clip our y-hat values. In this case, there's no change from the initial y-hat values. And then, we'll calculate the negative log of each sample. Finally, we'll use NumPy's mean function to get the average categorical cross-entropy loss for this forward pass. In this case, the loss after our first forward pass is 0.73. Alright, so that was the entire forward pass, and ultimately, it was just a function. A deeply nested one, but a function nonetheless. We dotted the inputs with the hidden weights, added the hidden biases, ran the result through a ReLU, dotted the result of that with the output weights, added the output biases, ran the result through the softmax, and passed that and the targets to the CCE to get the average loss. We now need to adjust the weights and biases so that hopefully the loss is lower on the next forward pass. This is where backpropagation comes in. We need to adjust 4 sets of numbers: the output weights, the output biases, the hidden weights, and the hidden biases. To do this, we need to figure out the gradients for those weights and biases. Since we're working backwards, let's focus on the output weights and biases first. The gradient for the output weights is given by the derivative of the loss with respect to the output weights. And as we saw in the slides, we can figure this out using the chain rule. In this case, the chain consists of 3 components: the derivative of the loss with respect to y hat, so the output of the softmax function, the derivative of y hat with respect to h2, the output from the output units, and the derivative of h2 with respect to the weights. And we can get the gradient we want by multiplying the 3 together. For the loss with respect to y hat, we need the derivative of the categorical cross-entropy function, and for y hat with respect to h2, we need the derivative of the softmax function. But the cool thing is that the product of these 2 derivatives works out to y hat minus y, which gives us the loss with respect to h2. So just by subtracting y hat from y, we take care of 2 of the terms. We won't step through the proof of this, but if you're curious, these 2 articles explain it in depth. Alright, here are y and y hat respectively. We're going to do an element-wise subtraction. So the components of the first y hat row minus the components of the first y row, and so on. We'll also take the additional step of normalizing this using the dataset size. This is so the size of the gradient doesn't get affected by the size of the input. So now we have the loss with respect to h2. Alright, the last term to figure out in the chain is how h2 changes with respect to the output weights. And that's pretty simple. The derivative is simply whatever the output weights are multiplied with. In this case, that's A1, the hidden layer output. Now to get the gradient we want, we need to multiply this term and the loss with respect to h2 we calculated earlier. The tricky bit is getting the shapes right. The gradient needs to be the same shape as the output weights. The shape of the output weights is 4/2. The shape of the terms we need to multiply look like this. We can't multiply them as is because their inner dimensions don't match. To make it work, we need to transpose the derivative of h2 with respect to the output weights. In other words, we need to transpose A1. If we do that, we get matching inner dimensions, and the shape of the resulting output would match the shape of the output weights. That's all well and good, but does this make sense? Let's take a closer look. This is A1 without any transposing. Each row of this represents a sample. So this is the hidden layer output for the first sample, for the second sample, and so on. Another way of looking at it is that each column is an output of 1 unit for every sample. So this is the output of the first hidden unit for every sample. This is the output of the second unit for every sample. Just to be sure, the third column is the output of the third unit for every sample. Looking at the backpropagated signal coming from further in the network, so the derivative of the loss with respect to h2, each row also represents a sample, and each column represents the signal from 1 unit for every sample. So this is the signal coming back from the first unit for every sample. This is the signal coming back from the second unit for every sample. What we're trying to do is figure out how changing the output weights affects the loss. So here the orange lines connect the third hidden unit to both output units via 2 weights. So going back up here, to figure that out, we need to dot the output of the third hidden unit with each column of the loss with respect to h2. So this first component multiplied with this first component, plus the second component dotted with this second component, and so on. But because they're both in column format, we need to transpose A1 to work. So really, the derivative of h2 with respect to the output weights is A1 transposed. And we'll reassign it down here and take a look. Now each row represents the output of a hidden unit for all samples. And now we can finally multiply the two derivatives, and we have the gradient for the output weights. Later on, we'll multiply this with the learning rate and subtract it from the current output weights to get the new values to try. Calculating the loss with respect to the output biases is similar. The bias operation is a sum, and the derivative of a sum operation is simply 1. So we can pretend to dot a matrix of 1s with the incoming backprop signal. But we can get the same result by summing the columns of the loss with respect to H2, and that's the gradient for updating the output biases. Next, we'll find the gradients for the hidden weights and biases. First, we'll focus on getting the derivative of the loss with respect to the hidden weights. Again, using the chain rule, we need to figure out this chain of derivatives. We already figured out these last two terms here from earlier. That's down here. That's just y hat minus y, which is done. So the next component we need is the derivative of H2 with respect to A1, because A1 depends on the hidden weights. We also need A1, the output of the ReLU function, with respect to H1, and finally H1 with respect to the hidden weights. So let's determine how H2 changes with respect to A1. The derivative is simply whatever A1 is multiplied with. In this case, that's the output weights. Specifically, it's the output weights transposed. Why transposed? First of all, we need to transpose the weights so that we can actually multiply the matrices. By transposing the weights, we get matching inner dimensions. Looking at the output weights untransposed, each row of the output weights connects one hidden unit to the output units. So the first row holds the weights connecting the first hidden unit to the two output units, and this hidden unit's output is multiplied by these two weights. And as we know, each row of the backpropagated signal so far, so the loss with respect to H2, represents a sample. We're trying to figure out how a change in A1 affects the loss, so we need to dot the rows of the backprop signal with the rows of the output weights. But since they're both in row format, we need to transpose the weights to make it work. And so we'll do that down here. Now we have the loss with respect to A1, and it's a 5x4 matrix. Let's keep working backwards. Next in the chain to figure out is A1 with respect to H1, that is, how the output of the ReLU function changes with respect to H1. For this, we need to figure out the derivative of the ReLU function. As we saw, the ReLU is simple. It takes an input, and if it's greater than 0, it passes it through. If it's less than 0, then it outputs 0. So in terms of the derivative, if the input is positive, then the rate of change is constant. When the input is positive, any input change of 1 unit results in an output change of 1 unit. When the input is 0 or negative, there is no change. So the derivative is simple and given by this function here. If the input is positive, then the value is 1. If the input is 0 or less, then the value is 0. That's it. There are multiple ways to express this derivative in code, some more efficient than others, but a simple way is to create a matrix of zeros in the same shape as the input, in this case H1, and wherever H1 is greater than 0, set the same position in the zeros matrix to 1. And that's what we do here. So the bottom matrix is the derivative of A1 with respect to H1, and any place where H1 is negative, the value is 0, and any place where H1 is positive, that value is 1. Alright, now we need to multiply this with the backpropagated signal we have so far, which is the loss with respect to A1. Looking at their shapes, we see they're identical. And that's fine. The ReLU function is applied element-wise. There's no linear combination of any sort. So to get the loss with respect to H1, we just need to multiply the two terms together element-wise. And that's our loss with respect to H1. Alright, the last term we need to figure out is the derivative of H1 with respect to the hidden weights. And that's whatever the hidden weights are multiplied with, which is x. And specifically, it's x transposed for the same reasons we covered when we were calculating the gradients for the output weights. Now we can finally get the loss with respect to the hidden weights by dotting the remaining terms together. And we'll just check to make sure the dimensions of the hidden weights and the final gradient match. Finally, getting the derivative of the loss with respect to the hidden biases is the same operation as the output biases we calculated earlier. Alright, cool. So now we have all the gradients necessary to update our weights and biases, so let's do that. Using a learning rate of 0.01, we'll multiply each gradient with the learning rate, then subtract the result from the respective weights to arrive at new weight values to try. And that's the complete backward pass. We'll finish off this phase by doing another forward pass, this time with the new weights to see if the loss lowers. So all this logic here is the same forward pass code we used previously, all in one cell, except using the new weights. And if we work it out, we see the new loss is now 0.72, and it dropped from the previous loss of 0.73. Alright, so that's a complete forward and backward pass step by step. And while this is a good exercise to get a sense of the underlying mechanics, doing things this way is completely impractical if we want to try a bunch of different neural network setups. So for phase 2, we'll encapsulate all this logic in a set of classes and expose an API that's similar to what you find in PyTorch or TensorFlow Keras. And that'll allow us to quickly compose neural networks. So the first class we'll create is a layer dense class. There's nothing in this class we haven't seen before. So in the initialization, we'll pass in the number of incoming inputs and the number of units the layer should have, and optionally specify the lower and upper bound of the weights, and we'll use that to initialize the weights and biases. To perform a forward pass through this layer, we'll call this forward method, which takes inputs and performs the linear combination with the weights and biases. We're saving the inputs because we'll need them later to calculate derivatives. To perform backpropagation through this layer, we'll call this backward method, which will take the backpropagated signal from further layers and calculate the gradients related to the weights, biases, and inputs up to this point. Again, nothing we haven't seen before. And finally, we have this update method, which will update the weights and biases by multiplying the respective gradients by a learning rate and subtract it from the existing weights. Next, we have our ReLU activation. Again, nothing new. We'll cache the inputs during the forward call to calculate the derivative later, and that'll happen in the backward call. Since the softmax and categorical cross-entropy function are used together so often, we're combining them in one class to make the gradient calculation easier. Again, the code is the same. In the forward call, we cache the inputs, calculate the softmax, taking care to clip the y-hat values. We're also going to save the y-hat values because when we use the network for prediction after it's trained, we'll want these values. We'll calculate the CCE loss in this separate call here, and the backward pass is simple. Alright, so those are the three classes we'll use to compose simple neural networks. We're going to generate a classification training dataset using scikit-learn's make Gaussian quantiles method. Each input is going to have 3 features, and there will be 2 classes. And just because it's easier to visualize, we'll first generate a smaller dataset of 1,000 samples. Okay, so we'll visualize the dataset using matplotlib. I'll open a new tab here. Okay, so the plotted dataset roughly forms a sphere, with one class, the black dots, clustered in the center, and the other class, the red dots, mostly around the inner surface away from the center. Our neural network's job will be to learn how to classify an input into one of these 2 classes. Okay, so we'll generate a larger dataset for the actual training here. And this is what the first 10 sample inputs look like. And these are the targets for the first 10 inputs. And our dataset is in the form of a 10,000 by 3 matrix. As we did in the earlier phase, we'll one-hot encode our targets. The function here contains the same code we used earlier. And passing it our array of targets, we get back one-hot encodings. Alright, so now we can declare the layers of our neural network. We'll create a 3-layer network with 2 hidden layers of 4 units each. We'll call the first hidden layer dense 1 and the second hidden layer dense 2. Both hidden layers will be followed by a ReLU activation function. The output from there will go into an output layer of 2 units, feeding into a softmax activation and CCE loss function. Again, nothing new, and random.seed is set to 0 here so that you and I get the same output. If you comment that out, you'll get different weight initializations, but the end result will be more or less the same. By the way, using 2 hidden layers is probably overkill for this simple task, but I wanted to demonstrate multiple hidden layers, so that's why we're going this route. Once our neural network is trained, we'll use this predict function here to classify unseen data. All that's happening in it is the forward pass on the input. So the input goes into the first hidden layer, then ReLU activation. The output from that goes into the second hidden layer, and ReLU activation again, and finally into the output layer, where it then goes through softmax. And at the end, it returns the classes with the highest probability for each input. If we ran our balanced dataset through this untrained network, we'd expect about a 50% accuracy rate since the network would essentially be guessing. And that's what we see here. So far, no surprises. We'll now train our network to do better than 50% accuracy. We're going to train our network using batches of data over multiple epochs. We'll talk more about batches and epochs in the next module, but for now, an epoch is one complete pass through the entire data set. So here we're going to train our network over 30 epochs, and that number was chosen arbitrarily. For each epoch, the data will be divided into batches of 32. So a batch of 32 samples will be sent through the network during the forward pass, the weights will be adjusted, and the next batch of 32 will be sent through. And 32 was chosen simply because it's popular. We'll talk more about setting epoch and batch values in the next module. The code here divides both the inputs and one-hot encoded targets into batches, and it also takes care of the last batch not containing an even 32 samples. And just as a check, we'll make sure we have the same number of input and target batches. And that looks good. Alright, cool. Finally, this is our training loop, and again, it's mostly what we've seen so far. So we're going to have an outer loop of epochs, and for every epoch, we're going to process the data set batch by batch. We're going to accumulate the accuracy and losses per batch so that we can calculate an average for the entire epoch below. The forward pass hopefully looks familiar by now. After the forward pass, we'll add the loss for the batch to the list of losses for this epoch. Note that we're multiplying the return loss by the size of the batch. This is because the loss that gets returned by the loss function is an average already. Since we want to take the average of these batch losses later, we're undoing the average operation. Otherwise, we'll take an average of averages and the result won't be accurate. And here we'll calculate the accuracy for the batch as well and add it to the running list. Further below, we have the backward pass where we backpropagate the signal and calculate all the derivatives. And finally, we update the weights and biases via gradient descent. Once the epoch is complete, we calculate the mean accuracy and loss and output the result before moving on to the next epoch. Alright, let's kick that off. So right after the first epoch, we see accuracy dropped a bit and stayed low for the first few epochs while loss kept improving. Around epoch 4, the accuracy started increasing and the loss started dropping dramatically until about epoch 9, at which point accuracy was perfect and stayed that way until the end. Essentially, the neural network memorized the data at that point, and this is a clear indication of overfitting. If you're unfamiliar with overfitting, we covered the concept of overfitting in the Building Models module, and we'll talk about it a bit more in the next. Now, a few notes here. You may be wondering about the relationship between accuracy and loss. For example, why would loss keep dropping once accuracy is at 100%? This is because accuracy is a binary comparison of which class from the softmax had the highest probability and doesn't match the target class, while loss is the numeric difference between that probability and 1. So, if you had a prediction for a sample where the softmax output looked like this, 0.51 and 0.49, and the one-hot encoded target was 1, 0, the accuracy would be 100%, while the loss would be the difference between 0.51 and 1. If after a bit more training, the softmax output for the same sample now looked like this, 0.9, 0.1, the accuracy would still be 100%, while the loss would now be lower. Combined with some batches being harder to predict than others, this is how we can end up in situations with high accuracy and high loss. Our network has overfitted on this data, but is that automatically a bad thing? It really depends on the nature of the data and the goal. Let's generate some test data from the same distribution we used to generate the training data. So we'll generate 1,000 test samples. This is data the network has not seen. And if we run the test data through our untrained network, the results are still good. So in this particular case, overfitting wasn't a big deal because we know our input data is from a fixed, well-defined distribution. If our data was more unpredictable and variable, then we'd have to do something about it. In other cases, a network from a major AI company may be huge, billions and billions of parameters trained on terabytes of data. In that case, the network may have picked up so much knowledge and covered so many scenarios that despite indications of overfitting, it can still reasonably address most of the things we ask of it. Still, if we can get the same performance with fewer parameters, we should do it simply because it's more efficient in both storage and performance. We'll have more to say about this stuff in the rest of the course. The important thing for now is that we have a good idea of the underlying mechanics of neural networks, and what we've covered here is one way to do it from scratch. From here on out, we'll rely on frameworks for rapid prototyping and experiments, and in the next module, we'll cover a variety of details involved in training neural networks. In this module, we covered the neural network learning cycle and the core mechanisms involved. We looked at a neural network as a series of data transformations from feature inputs to prediction outputs, and various ways to calculate the resulting loss. This constituted the forward pass. We looked at how to calculate the gradient using backpropagation and how to update weights through gradient descent. We then applied our knowledge to build a neural network from scratch. And now you know the core aspects of how neural networks work under the hood. In the next module, we're going to look at setup details with neural networks, from selecting activation functions to setting learning rates, and a whole lot more.